Hello everyone, this is Group 26. For our final project, we are developing a tool called Identify. The goal of this project is to build an automatic ID photo generation system that takes a normal portrait photo as input and outputs a standard ID photo, specifically a frontal photo with a neutral expression and a white background, suitable for passports, national IDs, and similar documents. The pipeline consists of two stages: face normalization, adjust face direction, expression, and lighting using a GAN-based model; RMBG 2.0, a soda background removal model based on BiRefNet. The expected output is an ID photo that meets official photo requirements without requiring users to visit a photo studio or carefully prepare their environment. After our survey, we selected two papers that may serve as reference for our tool. The first related work we are going to introduce is a significant paper titled "Bilateral Reference for High-Resolution Dichotomous Image Segmentation," which presents a novel framework called BiRefNet. In the field of image segmentation, we are moving from coarse object localization to high-precision segmentation. This is what we call dichotomous image segmentation. The main challenge here is dealing with objects that have extremely complex and slender structures. Think of things like fine wires, hair, or architectural cracks. Traditional models often lose these details because they downsample images to save on computations, but RefNet was designed specifically to solve this problem. The core innovation of BiRefNet is its bilateral approach. The network is divided into two main modules: the localization module and the reconstruction module. The localization module uses a vision transformer backbone to capture global semantic information. Its job is simple but crucial: to identify where the object is within the large high-resolution background. Once the object is located, the reconstruction module takes over to refine the details. Unlike previous methods that just resize the input image, BiRefNet introduced bilateral reference blocks. This consists of two parts: inward reference and outward reference. Let's dive into the BiRef mechanism. The inward reference provides the model with source image guidance. Instead of resizing the whole image, it uses original resolution patches. This ensures that the fine details are kept intact and not blurred by downscaling. The outward reference is equally important. It uses gradient maps as a target reference. By supervising the model with these gradient maps, the researchers force the network to become highly sensitive to edges and fine-grained structures. In other words, the model is clearly taught to look for the boundaries of these complex objects. To further improve accuracy, they also use a masking strategy to filter out background noise that might have high gradients but isn't part of the target object. To train this effectively, the authors use a hybrid loss, combining pixel level, region level, and edge level supervision. They also found that multi-stage supervision significantly accelerates training, achieving similar results in only 30% of the usual training time. In terms of performance, BiRefNet achieved SOTA results across 13 different benchmarks, including DIS, high-resolution salient object detection, and concealed object detection. It is a powerful, generalized framework that shows how keeping original image details and focusing on gradients can push the boundaries of high-resolution segmentation.
We just saw how the first related work clearly separates the subject from the background, down to fine details like individual strands of hair. But the clean cutout still isn't a valid ID photo. If the head is turned or the person is smiling, segmentation alone can't fix that. These are really two halves of the same problem. One method handles the boundary between subject and background, and the other handles the face itself. That second half is our next related work, FNM, the Face Normalization Model from CVPR 2019. It turns a messy in the wild face into a frontal neutral one. Photos taken in the real world vary enormously. The head is turned, people are smiling, lighting is uneven, parts of the face are black. The authors observed that these variations badly hurt face recognition. Their idea was face normalization, strip away that nuisance variation while keeping the person's identity. The goal is to take a single unconstrained photo and output a face that's frontal, neutral, and still photorealistic. FNM was originally built to help recognition, but frontal and neutral is exactly what an ID photo requires, which is why it fits our project. FNM is a generative adversarial network, and the clever part is that it's trained on unpaired data. Normally you'd want pairs, the same person in a bad pose and in a perfect frontal pose, but those are very hard to collect. FNM avoids this entirely. It just needs two unrelated pools, a non-normal set of wild faces from Cassia Web face and a normal set of clean frontal faces from MultiPy. It's unsupervised. It never sees the ground truth, normalized version of any input. All faces are first detected and cropped with MTCNN. This design is what lets it generalize to extreme inputs. Just as the first related work leaned on a vision transformer backbone, FNM builds on a powerful pre-trained backbone too. But here it's a face recognition network. The generator splits into an encoder and a decoder. The encoder is a frozen pre-trained VGG face tool. The authors called it the face expert, and because it's already an expert at identity, it extracts robots' identity features no matter how distorted the input is. Only the decoder and discriminators are trained. There are two paths. A wild face X produces its normalized version X hat, and a normal face Y also produces a version Y hat. The discriminators then try to tell these apart from real normal faces, which pushes the generator toward realistic, clean frontal output. The paper highlights three novelties. First, the face expert network. Building the recognition model into the generator preserves identity through the transformation. Second, the pixel-wise loss. With unpaired data and only an adversarial signal, GAN training is unstable, so they use the normal face path. Since a normal face is already frontal, the generator's output for it should match the input almost exactly. That gives a direct pixel-level signal that anchors training. Third, instead of one discriminator on the whole face, they use a series of attention discriminators, each focused on a region like the eyes, nose, or mouth, forcing the model to get local texture right, not just the overall shape. You might remember the first related work used a hybrid loss combining pixel, region, and edge supervision. FNM follows the same philosophy and splits its objective into three terms. The adversarial loss drives photorealism. The pixel-wise loss keeps training stable. And the identity perception loss checks that the generated face still matches the input person in feature space. One detail. In the official code, the identity loss uses cosine distance rather than mean squared error. In experiments, FNM handles genuinely hard cases, large pose angles, heavy expressions, occlusion, bad lighting, and produces clean, realistic frontal faces. To put the two related works side by side, the segmentation method faithfully preserves every detail of the subject so we can place it on a white background, while FNM does almost the opposite. It deliberately transforms the geometry of the face, changing pose and expression while holding an identity constant. One protects detail, the other rewrites it under constraint. Together they cover both halves of an ID photo. Two caveats well engineered around. FNM only generates the face region, not shoulders or neck, and the official code runs on Python 2.7 and TensorFlow 1.8. With both methods surveyed, we can move on to how we combine them in our pipeline.
So we've now seen both related works. RMBG 2.0 gives us a precise foreground mask, even preserving individual hair strands. FNM gives us a frontal neutral face from any input angle. But here's the thing, they solve different halves of the problem, and naively chaining them together doesn't work. FNM outputs only a 250 x 250 face crop. There are no shoulders, no neck, and RMBG 2.0 needs a full portrait to correctly judge where the person ends and the background begins. So the real engineering challenge of our project is design the head, and that's what our pipeline is about. Here's our full pipeline. After MTCNN detects and aligns the face, we run FNM and RMBG 2.0 in parallel on different inputs. FNM receives only the tightly cropped face and produces a corrected frontal version. RMBG 2.0 receives a full aligned portrait before any FNM modification and produces a foreground mask. We then blend the FNM face back onto the original portrait body on stage 4, using the facial landmark boundary as a blending mask. Only then do we apply the RMBG 2.0 mask to replace the black with white. Finally, we resize to the target ID photo specification. The key insight is that stage 2 and 3 must run in parallel, not sequentially, because each needs a different view of the input. Let me walk through the 4 main challenges we've identified. The first and the most fundamental is the FNM crop problem. FNM only generates the face region, so we need to carefully paste it onto the original body. If the skin tone or lighting from FNM doesn't match the original, you'll see a ring artifact around the face. We plan to address this with Poisson blending, which smoothly interpolates pixel values across the boundary. The second challenge is a hair conflict. FNM might alter the hair region after correcting a tilt post, but RMBG 2.0 was run on the original hair, so if we blend FNM's output carelessly, the hair in the final image might look inconsistent with the segmentation mask. Our solution is to keep the FNM blending inside the facial landmark boundary, so the hair is always taken from the original photo. Third, RMBG 2.0 is a segmentation model, not a mapping model. Its output is closer to a binary mask than a soft alpha. That means individual hair strands against a white background might look slightly hard-edged. We'll apply a small Gaussian blur at the mask boundary to soften this. Finally, there is a practical compatibility issue. Official implementation is 5 years old and requires Python 2.7. We'll use a community-maintained PyTorch version instead. We have just 3 weeks until the demo on June 11th. Our plan is to spend the first few days getting each model running individually and verified. Then we build the full integration. That's where most of the difficulty will be. The middle week is for ablation studies and fixing whatever artifacts show up. The final few days are for evaluation and making sure the demo cases look clean. We expect the blending stage to take the most iteration time, so we've loaded it.